Good morning, everyone. I am S. Vijayalakshmi, working as a assistant professor at SNS College of Technology. Now we are going to discuss about implementing global register allocation in code generation. And so today we will explore how a compiler handles register allocation not just inside the simple code but across the entire program. So this process is called global register allocation, and it's one of the most important in modern compilers like GCC and LLVM. So have already seen tag based local register allocation. It works within the single basic block, already. Then each and every block also independently treated. Then now we are scaling that concept globally across multiple blocks and function boundaries. That's the global register allocation. And let the last end of the session we will know the global register allocation, and also learn how live variables and inference graphs and apply graph coloring heuristics, and also applies this knowledge to generate more efficient machine code. Then going to this session, like one example real world context. Imagine you are optimizing a game engine or a machine learning program where multiple functions share common data. If every function loads and stores variable from memory separately, the program runs slower than expected. So instead, if we are using the registers are intelligently shared among functions, performance improves significantly. So that's exactly what global register allocation achieves. And then, so the question is how to assign compiler allocate the registers efficiently across the whole program, ensuring variables that live the same time. So the solution, so many possible methods: graph coloring, past linear scan, and then heuristic allocation, and then live range sprilling coalescing. But we have the prototype as liveness analysis, and then inference graph, and also graph coloring. That is the step, and we have the overflow. Then first two step is liveness analysis. Liveness determine the live ranges of variables. Where are the programs which are the programs having the regions where a variable hold the value that might be used later. For example, suppose first the compiler identifies that a equal to b plus c, and then d equal to a into e. Print d means the first lines a and d are live. Once d is printed, then become dead. So this analysis helps the compiler to identify when the registers can be safely reused. Then going to the next step in interference graph construction. That means each node treated as a variable, and edge between two nodes, the variables are live at the same time and also can't be shared the same register. An edge between two nodes if their corresponding live ranges overlap. Then graph coloring. Suppose a and b lie together, edge a comma b is there. Then the goal is to color the graph is such that no two connected nodes share the same color. Then graph coloring means register assignment. If a K coloring found means each and every live range to the physical register corresponding to its assigned color. Then, if there are fewer registers than colors, some variables are spilled to memory temporarily. If the means not k colorable, some live ranges must be identified, and also to assign the variables to assign the registers after coloring. So, code generation with allocation. After coloring, the compiler map with each variable to its assigned registers. Example before allocation means A equal to B plus C means move R1 comma B, add R1 comma C. That means then compiler inserts, loads and stores for spilled variables. That means minimizing the memory traffic. Then spilling means storing less used variables in memory. Rematerialization means recomputing cheap variables instead of loading them again. So modern computers even rerun color graphing after spilling to balance usage. This makes global register allocation adaptive and then efficient one. Going to group activity, we give some sets of codes. We find out the minimum usage of registers, and also draw the inference graph, and also live ranges. Then summarize. Local allocation works within the basic block. Here we saw about that global allocation extends across the entire control flow graph. And the steps involved here as the liveness analysis, interference graph, and then graph coloring.